Hello, and welcome to the Mondays on Tuesdays podcast. I'm your host, Firecrow Silvernight, where I talk about Compare Basic, my project that keeps on projecting. And then later on, I talk about some interesting things. I'm very excited about what I have to say today. And the reason I'm so excited is because I'm going to talk about a word that I just made up, which happens quite a lot. But it's the difference between artificial intelligence and what I call AO, which stands for algorithmic observation. And so algorithmic observation, AO versus AI, basically is the numerical form of data science, and I'll go through a few different ones of them. It has accuracy, transparency, traceability, practicality, all things that AI in the form of large language models has shown not to have. So I'm super jazzed about this. I've had a few experiences from my programming past to talk about things that actually, for the most part, worked really, really well. And the update on Compare Basic is that I got the build system. I got the build system to build in a fantastic way that doesn't involve any shell scripts anymore. So I now can say that the promise of something that you can build only with a C compiler is true. And what's so interesting about this is that my experience of building open source tools is that it is so annoying to have something that you want to use, like an image library like libjpeg, libpng, or like a font library, libfont, or some component that would just be really cool to use, and then you want to download it, or you're like, I think there was one like super complicated audio application where I didn't have a package on my operating system, so I was trying to download something. And it had like so many dependencies, and a lot of them I had to compile from source, and every single one of them had a different build system. It was make, autocomp, CMake. I think one of them was Bison or something. Again, like programmer soup terms. But so what I have now is I have a C compiler. You compile a small bootstrap file, and that small file then compiles the rest. And what's interesting is that incrementally it uses different aspects of the Seneca system that it didn't have necessarily before. Now, this could get more elaborate with shared libraries, which I don't necessarily need right now, but that promise of you build it with GCC, which is the GNU very popular open source compiler, and it can tell that when you build it based on the flags that are passed in by the compiler. It compiles the rest in GCC. You compile it with CLang, which is very popular, not so GPL it's still open source. For those of you who don't know the sort of political nuance between the GPL and non-GPL open source, and that's more popular on Apple and FreeBSD. CLang is a little more modern, but it essentially serves the same purpose that GCC used to. Those are the two most popular targets. Then you have MSVC on Microsoft, and Intel has ICC, and I think there's something for embedded systems called like UCC. I don't know. I found some things in my research, but I'm very excited to say that it now compiles without a whole bunch of shell strips tying together. It is live, open source on the internet under BSD license. It's presently at github.com/comparebasic/Seneca, Caneka, or its forever home is Seneca.org, Caneka.org, and comparebasic.com has so much stuff. So crowdfunding does continue to lag. To be honest, it's mostly because I'm too embarrassed to crow about the system yet because it doesn't really run. But I should be a responsible business person and not just a developer and talk more about it. So if you believe in what I'm doing here, the sort of mission and vision, go to comparebasic.com and scroll down to funding, tell you all about it. But after the music starts, it will start in just a minute, marking the 5-minute mark and the end of me ranting about my own project. I'm going to talk about AO versus AI, which is algorithmic observation versus artificial not-so-intelligence. And here we go in a second as the music will play. So algorithmic observation is this really somewhat simple but fascinating concept. And the concept basically is that the combination of algorithms and observation is really where the magic happens, kind of like the combination of computer programming and human content is where the magic happens. I mean, if computers could crunch numbers and stuff, that would be cool, but it's really the combination of human content that makes them matter. It's when they download the web page that has some content that was, written by a human that you care about, and it sorts it based on the inputs you've given it, where you position the mouse, what you click on, the choices you make, the choices the designer of the site have made to allow you to make the choices you're making. And so that combination of human input plus, pre-programmed patterns is very important. Similarly, algorithmic observation is a very important combination because algorithms, we talk about the algorithm kind of like we talk about, I don't know, so like this is a random example, but supposedly the word cancer doesn't actually mean cancer. We all have cancer cells. Cancer has some fancy long name that basically transliterates into cancer out of control. But we just call it cancer, kind of like, there are name brand things we refer to. We don't necessarily say tissue, we'll say a Kleenex. When I was over in England, they don't really say vacuum, they say Hoover. Hoover's a brand of vacuum. And so we mix terms up a lot. And the term algorithm is like the algorithm is kind of like the social media opinion of what you should see versus what you maybe want to see. So what I want to do is talk a bit about what I consider algorithmic observation to be. It's not a formal term I've seen. I just think it explains what I'm talking about the best. And then contrast that against large language models, which is usually, how AI is considered, generative AI, art with people with 6 fingers and kind of mediocre writing that makes people feel like they're writers if they weren't, and if they were a writer, they look at it and say, "Oh, what is that writing?" And so algorithmic observation, I'll start by defining the term algorithm. So when you drive your car to work, the series of left and right turns is an algorithm. Now, it is a observant algorithm or a responsive algorithm if you change that pattern based on traffic. So you're changing up the rights and lefts based on the traffic. So now there's an observation in the algorithm that says, oh, hey, if I do this, I'll get to where I'm going. So algorithm, it's kind of a slippery term, but it basically just means a pattern that does things. And cleanest example is if you are shown 15 things on a social media site and you click 3 of them, it can observe that it should show you those authors of those 3 the next time. And where this gets really, rhythmic and the sort of the algorithmic part is it then compares what those people have in common possibly and scores that. And it might show you people that are not those 3 people, but have a similar score of a similar attribute in a certain way. It makes sense. I want to talk about 2 really interesting, well, 3 actually, 3 really interesting things. So they have, techie terms, but it's an NGram, it is a Co-occurrenceMatrix, and it is MapReduce. And I'll start with MapReduce. They're all 3 kind of different, kind of related. I'll start with MapReduce. So MapReduce is basically the way that big data companies crunch large amounts of data without completely blowing out the memory and capacity of the servers, because they can basically drip feed the calculation process. And an example of that is if you take a receipt, let's say you bought, I don't know, 5 or 10 things at the grocery store. And the MapReduce process would be take each individual item and treat it as an individual number. That's the mapping process. It says, okay, item 1, $5, item 2, $7, item 3, $6. And then it would total them up, and that's the reduce phase. It's called the reduce phase because it takes the first number, and it starts with 0, and it adds the first number to 0, which obviously is the first number. And then it takes the second number and adds it to that total, and adds it to that total, and adds it to that total. And in this way, it only has to touch 2 numbers at a time because you have the total in the next number. And now if you wanted to calculate only the dairy products you purchased, the map function would say, first item, $5, jug of milk. Next item, let's say, I don't know, $4, pack of hot dogs. So what it would do at this point is it would map those 2 things to different places. And then the next item, sour cream, 325. Cool. Okay, map it to, the dairy section. And then at the end of this, it would take each category and reduce those categories, and you'd get the totals of dairy, totals of meat, the totals of other things. And this is fantastic for segmenting statistics in a very sort of low-cost way. It's called MapReduce. And I was at a company around about 2010, and they were using this to figure out what email marketing to send to people. And they were doing it based on a genomic analytic algorithm that the founder had seen in college, and then decided, though, hey, I'll apply this to marketing. And that carries a lot of weight. Oh, genomic. Oh, but the thing is, the statistics actually predated the genomic stuff. That's just what they were using. It's actually the history of mathematics. That's really amazing. And I tell humorously a joke. As cool as it was, it just means that the marketing emails you weren't going to read, you're still not going to read. But the thing about this company was that they were able to take what's called clickstream data. So people clicked on the site and map it into categories of categories of categories through this MapReduce, and come with a pretty convincing idea of what you could send them they'd be more interested in than one product newsletter for all. And then the next technology I'm going to talk about is the co-occurrence matrix. And the co-occurrence matrix basically is a very, very fundamental way of figuring out the overlap between data things. So it's somewhat intuitive, but a co-occurrence matrix basically is if you take, let's say you have a series of 5 friends. We'll call them Tom, Joe, Sarah, Malcolm, and Jessica. Okay, so I probably will not remember those names, but what you would do is you have Tom, Sarah, Jessica, Malcolm across the top. I know there's a 5th one, but I forgot it already. And then you actually have Tom, Sarah, Jessica, Malcolm across down the side as well. Now, this is so strange because when we think of tabular data, like in a spreadsheet, you think of like the categories across the top are like the date of something and the item and the location and the cost. And then down the side, you have, what the item was. To dinner at this location, this much cost, this date. To the movies, this location, this much. Right? Like that's how we think of tabular data. We think of it as a 2-dimensional map. First dimension is those categories of cost and location and date. And the second dimension is the items themselves. The name of the item, what happened. Well, a co-occurrence matrix is a 2-dimensional matrix where both dimensions are the same. Bum, bum, bum. How does that work? Like, what's the point of having them the same? Well, I'll tell you why. So back to that analogy of the 5 people. Let's say these 5 people were sort of loose business or social acquaintances, and you wanted to figure out who was most commonly at locations together. Well, if 2 of them intersected in the same location, like if Jessica and Malcolm were at a party together, you would just take the cell, which is 3 over for Jessica, 2 down for Malcolm, and add a 1 there. And the next time they're at another location, you increment that to a 2 and a 3 and a 4. And you do this for everyone. So it's the correlation of dimension 1, dimension 2 having the same values. When do they intersect? And pretty soon what you have in this like 2-dimensional matrix is the high numbers represents a high concentration of overlap between the people at different events. So there is a 3rd dimension here that's not represented on the spreadsheet, which is the events themselves, and that can lead to complicated multidimensional things, but it is a trackable thing. So how this maps into algorithmic observation is that with MapReduce, you can very quickly bucket totals of things that occur in the same place. And then with MapReduce, you can very quickly bucket things that happen in different places, but co-occur a number of times. And with these 2 things, you can start to see the relationship between things. So how does this work for, say, analyzing a paragraph? Well, if certain words appear in the same sentence, that can fit into the co-occurrence matrix. And if certain words appear a lot of times within one document, that can be filtered with MapReduce. If you click on the things shown to you, it's probably using both to figure it out. And the advertising industry is doing a whole bunch of this stuff to figure out what to show you. But there's a lot more value in this sort of simplistic way of doing, you know, AO, which is algorithmic observation, because these are such fundamental numerical constructs that you can reason about them. You can say, we got the data from here, right? We were slicing the combination this way. We have these business insights based on something we can prove, and we can look at the original. And if you combine that to a large language model that's quite literally just taking tons and tons of stuff to the point where you have no idea how it comes up what it comes up with, the cost to business decisions through the inaccuracy and the sort of confusion of that, and the amount that someone is beholden on the vendor that wrote this crazy, graphics card intensive thing, it's so much higher, it's so much opaque, and it's so much less accurate. One of the reasons it's so much less accurate is because it's language based instead of numerical. And there's a fantastic book that I haven't actually read. It's called Eats, Shoots, and Leaves. And it is all about how terrible grammatical mistakes can make the English language. And it's got this wonderful cover of a murderous panda with a pistol. And then I think on the other side of the cover, there's like a panda eating like bamboo or something like that. And the joke is eats, comma, shoots, and leaves literally means he, eats, pulls out a pistol, shoots somebody, walks away. Whereas eats, shoots, and leaves with no comma means that, that's part of his diet. Pandas eat, shoots, and leaves. And so, oh, here's another one of my favorite examples. So the terms viewer, watcher, and seer when related to all aspects of television and movies. So, when's the last time you told someone you really enjoyed seeing a movie? But are you going to say, "Oh, I'm a seer of that movie"? Like, you're a viewer of that movie. You're not even a watcher, even though you're watching the movie. I mean, like, there are so many things about the English language that are just like insane. And the idea that we're going to throw this through a computer and have it figure out the correlation based on a massive superset of the basic technologies I told you about now. But the problem that I have with artificial intelligence is that it seems to me like the sort of mixing colors problem. And the mixing colors problem, I was an oil painter very briefly. My partner does pour painting acrylic, and she's fantastic at it. I as an oil painter was not amazing. But I remember mixing colors, and you add a little bit of color, you add a little bit of blue, you add a little bit of green, and it's not quite right. So you add a little bit of yellow, and inevitably, I always ended up with shit brown. And so this idea that more is always better, that more big powerful AIs that have more data, it really drives further from value rather than towards it, because you're watering down the traceability to such a large degree. And there's something I've been kicking around for a very long time, is the idea that we don't all commute in sports cars because they're impractical in how much gas they guzzle. They're not a lot of fun to drive in traffic, especially if they're a manual transmission. And so this bigger is better is not, it's not always a thing. It's just not always true. And one of the things that I think really could happen with these algorithmic observation products is that most of what I see algorithmic observation applied to is social media and marketing. But there is a huge value in smaller spaces like, it's also used quite a bit in search. And I did say I was going to talk about an NGram, so I will do that now. So an NGram is basically, you can think of it like a upside down tree that has one root for each letter of the alphabet, A through Z. And then, branching off of those alphabets, it is a branch, one per each letter. So an alphabetic, in the sort of Latin alphabet, an alphabetic anagram would have 26 feet. And then each foot would have 26 feet, each foot would have 26 feet. So you take the word like this, the, squid, and weather, right? So this, you have T, and then the same T. Hey, they blend together. H, same H. Hey, blend together. And then I, Well, I and E not the same. Okay, branch off different feet. So it'd be T shared, H shared, I different, E different, and that's the end of a word. And then S. So this and the THIS branched off. So you have I, S, and E as like separate things. And then squid would be, start from the letter S and, all the way to squid. And the way spell checkers work, I humorously call them small character models as the original AI. um, the way a spell checker works is basically it takes, it gets along that sort of tree path into completing it. It starts looking at, okay, if I go all the way down to the end of my feet of these overlapping words, how many possible completions do I have? And that obviously is only going to complete correctly spelled words. And so then what it starts doing is saying, okay, well, I have all these like jump off points between different, foot options. And people commonly switch the same sort of letters. They switch A's and O's, E's and I's, that kind of thing. And so if it sees a word that it doesn't have a lot of like hits for in terms of content, it starts to substitute these things. And because of the structure of the NGram, it's not that hard to switch one or two letters and climb around and see if there's a completion. And that's more or less how a lot of search autocomplete and spell checkers are built. And so when it comes down to artificial intelligence being this like super predictive thing, algorithmic observation could create a lot of composition by something called taxonomies. And taxonomies is basically just how you slice, dice, and categorize things. Interestingly, I remember when I was working at Shutterstock, we were working on co-occurrence matrices for, well, I personally wasn't, I was a front-end engineer, but there was a team, there was a fancy search team working on two things, co-occurrence matrices and facets. And the co-occurrence matrices they were doing were things like when French people search for fancy photos of tuxedos, they don't want to see pictures of people smoking because the something about the French word for fancy and cigarette smoke is related, and so they were like not so happy, and so they did a co-occurrence matrix where they took all of the keywords and looked at the overlap, and if the overlap of the keywords lent towards like a fancy photo, that's where it got bucketed. If they overlap to something else, they got bucketed as you are in fact looking for a person smoking a cigarette. Something similar with the German word for ocean. I forget what it was. The language was one of the best things about being a front-end engineer at Shutterstock was that it was translated into about, I think, 8 or 9 languages. And so we had to put translation tags everywhere, and then all of the designs had to be tested for like really long, really long German words and really long Russian words. And I think they were talking about Thai and Hebrew. Those are like the big crazy ones because I think they're backwards. Of course, according to them, the rest of us are all backwards. And so Shutterstock was doing this co-occurrence matrices stuff to help their search engine. And I wasn't on that team, but it was a very inspiring team. And then the team that I was on, we were doing a lot of A/B testing. And A/B testing is when you release different versions of the site to a small group of your customers and figure out what they are. And I think we made like 9 variants of one page at a time, and then they had a cumulative statistic graph to figure out, which one was making the most money. But the other thing that we were doing is we were doing a lot of facets. And facets are when, like the best example I have is you go to a site and the site sells, maybe you want to look at refrigerators. It's like an appliance store. And it now says, okay, if you want to choose by color, there are 3 that are black, 15 that are white, 4 that are some other color, blue or pink or whatever. And then if you want one with a glass door and you select glass door, okay, now we only have 1 that's black. We have 2 that are silver. So facets are that drilling down thing where you select something. And as someone who uses computers and goes around the internet, it seems so boring at times. It's like I'm looking for something and I'm like, I know that this person blogs about like 15 different things, and I'm trying to find an article I had read, and I know what the subject is, and there's no way to search by tags. There's no way to filter this content. And it is, I think it would be so relevant to have that real rich sort of search and filter feature on, a website engine that's accessible to everybody. And I was going to limit my my shameless plugs for Compare Basic till the end, which is coming near. But I will do two of them. The first shameless plug is this is one of the inspirations between the first product I expect from Compare Basic called Email to Site, which is the ability to give people insights based on how people are using their site to suggest navigation hierarchies, as well as provide taxonomy to users. And I'll give you a quick example of how algorithmic observation and taxonomies could work. So the first example site will be my cooking blog, redneckramen.com. And it's basically, all the sourdough and baked potatoes and homemade pasta and random mix-ups of, South Asian curry and Southeast Asian sort of vegetable dishes that I have, made over this 2 years of living my best broke life, as well as a number of strategies for how to do the dishes effectively, which, given that I was, I can call myself a professional dishwasher now. I have ways I like to do the dishes where I can clear a kitchen real quick. So Redneck Ramen has a few different audiences. It's always how to cook on a tight budget and get the most of it. But depending on what that means, you are either broke for time or broke for money, and they're very different things. Because if you need 10, 20-minute recipes, I got them. If you have 3 hours to roast a whole chicken, I got that too. If you have 48 hours to make some sourdough bread, I got that too. And so, if you're vegetarian, if you eat meat, if you don't like eggs, and all of these categories are something that I can surface as taxonomy things to click. And then as I get a sense of what the overlap is, there are some vegetarians that still eat fish. There are some vegetarians who will not come back to a site if they see an image of me butchering a steak. So um, I think that this kind of taxonomy is something I would really want as a hobbyist talking about my cooking. Um, and what I hope with the email to site product is that it can just be like a jumping off point for people to really talk about their passions, show slideshows. Um, and to me, that means that it does need the, search, sorting, filtering, and, algorithmic observation aspects of like, a high-end commercial e-commerce site. Um, and when I look at the sort of AO versus AI debate, on one side of AO is that it's relatively simplistic, and so you do have to somewhat explain where your observations are coming from. You have to like say, okay, we're analyzing this now. Whereas AI, you can just kind of like shoot the moon and hope it comes back correctly. But on the side of AO versus AI, AO is so much more concrete, so much more reasonable, and so much more actionable. And it really supports taking action, whereas AI tends to want to do the actions for you. And that's wonderful in certain cases. But as a family member used to say, but does it do the dishes? Um, that's uh, that's the end of this podcast. I think I had an analogy that I guess I'll share quickly. It's the idea that we've been screaming operator into our phones to AI bots that can't read our voices for 30 years, and that has never changed. It's like operator, operator, and not in the cool Matrix kind of like I got to get out of the Matrix, but just like get me a person. So let's hope that the AI bubble has a little bit more traction and is a little bit more responsible than those automated menus that pick up the car that drives by me rather than the choice that I've made. Um, so if you, yeah, if you like the stuff I'm talking about, think the Sonika system has a future as like increasing transparency and stuff. Head on over to comparebasic.com, and if you'd like to contribute financially, there's a funding link at the bottom. And I will see you next week.